want to try to get through this quickly for you. I know it's been a long road getting here. First thing I want to do is, rather than put the whole radio up here and try to use the radio's power supply to power this board, I don't need to do that. I could just take an ohm meter and go across these pots and set these pots to their minimum or maximum level as we've determined they should be for proceeding. But I want to do more than that. I want to actually test this regulator. Remember from the schematic, we came in at 13 volts, went to the regulator fed all the bias circuitry. And I want to test all of that. I want to know that the actual bias voltage is correct. There's no bad diodes, no open reference devices, anything like that. So we're going to take our laboratory power supply, which is, current limited and very, very well regulated, and we're going to connect it. Now it should be connected to a little jack over here, a little plug, but that same point of connection is right here. So there we go. We've got our power. Got my scope ready to go, and I also have my my meter, my digital meter, ready to go to give you an exact voltage where necessary. So first thing I'm going to do is I'm going to flip on my 13.8 volts, and I do not see any indication of current flowing from my bench supply at all, which is excellent. And then we're going to go right to, well, we can look right here and look right here, and sure enough we can confirm our 13.8, 13.79, and we should have that, I believe we should have that here. Yes, we do. Pin 1 of that device. And the output of that device is probably over here. Let's go back to the schematic. I need to review what I'm looking at. Okay, so it does not show pin numbers on the regulator. It shows in, out, on, off, and ground. Ah, on, off. So we need an on-off signal to that pin. So we're going to turn off our 13.8 volts and see if we can't look at what T9 is. Okay, so a quick check on this device. It is it's specified in the parts list as a PQ09TZ1U, and which is a voltage controlled or logic enabled voltage regulator. Now most times when you see bias switching in these radios, they will simply use a series pass transistor to supply bias current using a control voltage to switch the transistor on and off, which is a very simple, easy way to do it. This, however, is eliminating that part and replacing it with a more proprietary part. As soon as I saw this switched regulator, I said, oh boy, this is going to be one of those items that, if it goes bad, you're not going to be able to replace it because it's probably discontinued. And sure enough, I looked up the part because I wanted to see what the control voltage requirements were, because I'm going to have to enable this with a control voltage. And sure enough, the part came up discontinued on everybody's website when I looked for the PDF document on the device. So there you go. If this chip were to blow out, if this regulator were to smoke, This would probably have to be replaced with a simple 3-terminal regulator, 7809, and we would add a switching transistor ahead of it, something capable of delivering, well, a couple hundred milliamps. So maybe probably not a TO92, but maybe something a little bigger, but not much. And it is indeed enabled with a switched 9-volt control signal from the control board. So there's a couple of ways that we can supply our enable voltage here. Okay, so what I'm going to do, I'm going to make life simple for myself. I could probably pull 9 volts out of the supply, but I'm going to make life simple for myself. So what I'm going to do, I'm taking a 47,000 ohm resistor. It could be 100K. It could be almost anything. It's the logic input on the input is greater than 2 volts, and for a logic 1, and 200 microamperes of current. So it's basically just a low level logic signal. So I should be using an even thinner wire rather than my probe here. Just going to get a few turns. So that becomes my logic signal. Press it right onto the pin there. Okay. And that's pretty snug on there. Good. So now we're going to turn our power supply back on. I'm going to take my voltage probe and the voltage which is supplied right here very readily, and I see 0 volts at the moment. So if I connect this to my 13.8 volts and I connect this to my enable, I should see 9 volts and enable. Yep, 9 volts. Now, what I do not have is I do not have class AB transistor activity. Now, we know that requires there's 2 switching transistors to pull the class A bias down to achieve class AB. Those transistors are not enabled at this point, but I do have my 9 volts. Is I'm going to put my scope probe on the gate connections of my finals, and you see I have what looks like 4, almost 4.6 volts on that one. Well, let me zero it because it's not quite zero it. Actually, let me do this with the meter. 4.3, and the other one is 4.3, 4.33 and 4.339. Pretty close. That's pretty cool. And 4.48 for the driver. So it's nice to know. And that's going to be class AB. So let me go back to the scope probe so you can see what I'm doing. Going to arbitrarily pick a device here, and I know that these are my two class A devices here, so I'm going to turn those, and you see the voltages go up and down. These pots feel funny. They don't feel like I'm getting, okay, yeah, I did feel it stop. They get stiff at the ends. So I'm able to get between 3 and 5 volts out of them. And I'm going to do the same thing on the other side. I'm going to get 3 to 5 volts. So I would say both of those circuits are working fine. I'm getting the same thing on both of them. It makes sense to me. I'm also going to play with the class AB pots, and I see no change there whatsoever. And minimum bias is counterclockwise. So my original reading of the schematic would have been wrong, which is why I do this. And if I go back and review that again, I'll probably look at it and say, oh yes, of course, you dummy. But this is the better way to do it. So reduce the voltage. Let's go do the driver. I'll go to the driver here, and again, counterclockwise. This one goes much lower. It goes to about 5, but it comes down to almost 2. Okay, so minimum there. And that should be sufficient. I don't necessarily need to adjust the AB values at this time, because the A values are the higher values, and that's what really drives it. And the AB values can only be lower, and I'm not really worried about them not functioning, quite frankly. And I am going to check one more thing. I am going to go over to the driver, and I'm going to look at the value on the base of the driver. And you see, I said we should have a little over, I think I said in the vicinity of 0.8 to 0.9, 0.8 to 1 volt maybe. And it looks indeed that it looks to be exactly what we have. In fact, I'm going to put the meter on it, and I see 0.79. So that's a nominal voltage. If nothing else, it doesn't necessarily tell me that the device is good, but it does tell me that at least I know I don't have a punched gate. I don't have a shorted gate. I should see nothing on the drain side or the source. That's probably the drain. This would be the source. And that should be fine. Okay, so I am now totally comfortable putting new transistors in here. So let's get to it. Let's open the box. Take out the little magic devices that still have their smoke in them. So it's time to put these parts back in. Now, here we have the old parts. These are definitely junk. And I just want to make a quick announcement for at the sake of being overly cautious, perhaps. But these devices, and frequently external anode tubes, like the 46250B and the like, the ceramic that is used in these frequently contains beryllium oxide. Now, these are newer devices. They may have changed the formulation and they don't contain beryllium oxide. The Chinese shippers, manufacturers, suppliers, what have you, probably are under no obligation and have no inclination to send a little warning slip of paper in the box. But I believe if you would order these parts from a U.S. source, you probably would receive a little red slip of paper that's saying, "Warning! Contains beryllium oxide. Do not sand or crack or break, or do not do anything that's going to create small particles of this ceramic." In other words, don't take these apart to look at the dye inside. Don't play with them. Beryllium oxide will kill you. It is highly carcinogenic if you inhale it. So don't play with these. Okay, so there's your PSA for today. Let's solder the new ones in. Okay, so now we need to put some heatsink compound on these devices. Dab will do ya. That's more than enough. Now the dye inside is right there. That's where all the heat's going to be generated. But we're gonna spread a thin film everywhere, and it's just going to be a really very thin film. You don't need a lot. So, and a little dab right in the middle, and that's that. You want to make sure you mix this stuff up well, which is why I have mine in a cup, so that I can mix it up. It is aluminum oxide powder for the most part, which is suspended in a silicon oil matrix, and the aluminum oxide will settle out in a tube if you're using it from a tube, and frequently the oil will come out first. The oil is not a terribly effective thermal conductor. By the way, you see a little black streak there. This aluminum oxide, it's the same aluminum oxide you find in grinding wheels in a machine shop, and it is very fine, and it actually makes a pretty good polishing compound. If you look at that, if you can see that. So, polishing compound, pretty good stuff. And 6. And this is why I don't use demagnetized tools. It's just, if this wouldn't come off of here, I'd find that very frustrating. Get my screwdriver. This is the wrong screwdriver, by the way. 60 degrees, not 45. Japanese stuff. It's also too small. Looks like the right size screwdriver for that screw, doesn't it? Yes, the right size screwdriver is always a size larger than you think. I am reluctant to tighten screws, even steel screws, into aluminum. If they don't want to go, there's something wrong. I hate taking apart radios where people have cross-threaded or forced screws into holes simply because they'll go. It works. It works. No, not really. So I'm gonna tell you one of my techniques here. Not really a secret, but something that has served me very well over the years. And it's applicable to screws, both machine screws like these, or more importantly, sheet metal screws and screws that are put into plastic. When both plastic and sheet metal screws are used, they usually cut their own threads. I mean, there's no, you've never heard of a sheet metal thread tap, right? Or plastic for that matter. In fact, plastic screws usually have that little tooth cut into them. I'm tightening these slowly, like you torque down an engine head. I like to give the time. I like to give the heat-sinking compound time to squeeze out, because when it gets really thin as you're tightening, and when it gets really thin, the pressures can build up quite high as that fluid slowly seeps out underneath the die. If you just crank these down tight, all of a sudden you're going to bend the device. You're going to put a bow in the base of the device. So we tighten them down nice and slow, and so when you put a sheet metal screw in or a plastic screw in, it cuts its own threads. That's the point I'm trying to make. And if you just put those screws back together, you're liable to cut a new set of threads or a second set of threads. And if you continue to disassemble and reassemble, you're liable to cut many threads in whatever they're going into. And if you continue to do that, you will open up that hole until there are no more threads and the screw does not hold anymore. So, little trick, very simple, very easy to do. When you put the screw in, don't screw it in. Screw it backwards. Very gently, with very little pressure on it. Turn it backwards. At some point, the threads will slip off of each other, and you'll feel like a little click or a little jump. It'll sort of jump down into the hole. It'll jump down and align itself or synchronize itself with the original thread, and then you screw forward and tighten it up. And if you do that every time, you will be putting the screw into its original threads each and every time, and it will hold with virtually its original retention capabilities each and every time. So you can take something apart many times and not end up with a plastic case that falls apart. So put the screw in, go backwards till you feel a little click, and then screw forward. It's little things like that that make the difference between a good technician and a great technician. I'm still working on great. I'm comfortable calling myself good. Okay. See, when I go back and turn these screws, it feels like they've loosened up. And it's just the heat-sinking compound oozing out. And I'll probably get one more turn out of that. I do have a little device here, a torque screwdriver. What do I have it set to? I think I have it set to, looks like 3 inch-pounds. And that's probably what we're going to end up with. You hear the click? 3 inch-pounds. This one I'm going to have to do by hand, which is okay. I'm comfortable with that. Okay. But again, it's a luxury item. It's a tool that you don't absolutely have to have, but you should have a pretty good feel. You don't torque these things down like submarine hatches. Okay, time to put some solder under these devices. Now, a little word about solder. Some of you very likely can no longer find leaded solder. If you're buying it commercially, it's pretty much unobtaining them now. And so what you find is the lead-free stuff. And it works. It's okay. Just, you know, be aware that it has most of it has a slightly higher melting temperature, and it's very fluid. It does not tend to wick in between the parts or on parts as well as the lead solder. So if you're soldering things where you're in a position where the solder may run away, it may in fact run away. Okay, my soldering iron is up to temperature. So we'll go for the low-hanging fruit first. I'm soldering to the circuit board. This tab is very thin. I don't really need to apply heat there. I need to get the circuit board flowing. Okay. I can see that's fully wetted underneath. Don't need huge blobs of solder. There we go. So I'm applying the solder under that tab. Now by assuring that the solder is going under the tab, I know that the rosin is getting in there and doing its job as well. Okay. So, good contact, good flow. Okay, let me zoom back a little bit here. we're going to check these parts quickly. Now, there's going to be some error here because I'm using test leads. I don't have quite enough. Oh, I might as well just toss these up here. I don't have quite enough leg on the part here, nor do I want to straighten them out and bend them and rebend them. And these are 221, so 22 plus 10, so 220 picofarad. That's a little over this scale. 200 puff, 2 nanofarads, or 2000 picofarad. And let's see what we got. If I can get good contact on. There we go. 253. 0.253 nanofarad. .216. That's 215 puff. And 254 puff. I don't like that. So I'm going to go into my bag of tricks and try to find another one that's more in line. Two capacitors here that no longer meet specification that we took out. So now we're going to replace them with back up a little bit. I'm going to replace them with two new devices that are within a few percent of each other, and I'm going to just going to tin them slightly. Just to help tack them in. I did change to a thinner tip, a little longer reach, a little higher temperature too. So we'll tack that in here. Okay, so we've got our PA and the chassis all set up, ready to go. The power supply is under the desk. I didn't hook up the power supply yet. That's a separate component with this radio. But I've got my 50 ohm dummy load on the output of the PA, just in case there's any tendency whatsoever to generate anything. We don't want the output to be unterminated. If there's any little bit of signal there, an unterminated output can turn that into a severe parasitic self-oscillation, and it could be catastrophic. So you always want something on the output. There are bypass caps and the like that do tend to suck up some of the real high frequency stuff, but nevertheless, like I said earlier, we're going to have dummy load on the output. Now for the input, for the dummy load and the input, we have these little I'll just show you here. We have these little plugs. Focus you. We have these little plugs, and they go into these little connectors on the board, as you can see here. So what I'm going to do to mitigate that is I have these little BNC dummy loads that I made up quite some time ago, and if I take them apart, inside they have a center pin which is just about the same size as the center pin on this power plug, and they're about the same diameter behind that too. So we're going to we added a little insulation, we put some thin heat shrink on here, and It fits in very nicely. I just slide it in there and push it home a little bit, and it just works out that the back, the cap, is quite firmly pressed against the chassis. So I'm not even going to do anything further to ground that. I'm just going to leave it as it is. That should be fine. So there you go. So there's our dummy load on the input, and now we're ready to proceed with tuning this thing up. I'm going to have to set up another meter here. I did want to put the camera on my bench meter, but neither of both my bench meters are precision meters, and they're really not made for anything over an amp. I mean, their claim to fame is, you know, accurately recording microamperes. So let's see. We're gonna find probably a good old Simpson 260. In fact, I think I'll use my. Let's see. I've got a few of these. I think I'm going to use my favorite vintage 260 with the timbre case. Isn't that a beauty? If you don't appreciate that, you're in the wrong business. Yep, but that's what we're going to use. On the 10 amp scale, we're going to be drawing 5 amps per device for Class A bias. So we'll get that set up right next to us here, and we'll try to get the camera up above to view that for you. Okay, so we're all set up now. What we've got here is the for the driver, the two pins are very, very close together. So I just stuck a little piece of paper between the clip leads there, and we're ready to make that adjustment. And hopefully you'll be able to see this meter here. So we're just going to go in there and do that. I think you can see that. And I'm going to put this into the transmit mode. By the way, the power to the finals is open at the moment. It's disconnected. And here's our driver adjustment. And I'll turn it up. And the needle just barely begins to move. There we go. Needle begins to move. I'm about 600 mils, 7, 8. That's 1 amp. 1.2, 1.4, and 1.5. Pot's a little touchy. I'm going to go over a little. Come back down. I like that better. Okay, so there's our 1.5 mils on the driver. Take it out of transmit. I'm going to shut down the whole radio. I am now going to connect to the final supply, and I'm going to power up. It seems to power up in Class A, so I'm in AB now. I see nothing. I should see nothing. If there's no Class A, there can be no Class AB. We're going to flip the switch. Okay, there's a little switch here to flip the bias from one device to the other. Okay. Going to turn on my Class A mode, turn on my transmit mode, and I'm going to make my first adjustment. and it's coming right up. Okay, I'm going to stop there for a moment. I want to comment on something here. I'm going to be very careful about feeling for heat at this point, because the way this is designed, my heatsink, right now my heatsink is resting on the tabletop. So it doesn't even have convection airflow from underneath. It's just sitting on a tabletop. I have to get to the adjustments inside the board here, which normally would be down facing into the radio. The fan for this unit is in the radio. Not a very good situation, because 5 amps on these drains at 30 volts. I kept saying 48, but it's 30 volts. But it's still 150 watts per device. So we're gonna get warm here. All right, let's do this quickly. 5 amps. That would be half scale. And stop. Go to the other position on the switch. Do that again. 5 amps. And stop. Okay. Take it out of Class A mode. I've got about 1.2 amps on that one, and about a little less than an amp on that one. So that's kind of nice to see that without doing any other adjustment, it's just about on spec. One amp. And I just realized I have to go back to my previous adjustment for driver, because I set it to 1.5 and it's actually 1.3. Okay, 1.3. There we go. 1.3. So that's it. These finals have been changed. They appear to come up nicely to spec, and I'll bring you back when we're ready to do the final test and final transmitter test. Okay. Got something to show you all. Wish I could do a wider view on here. This is all ready to go. Before I can put this back together, all these wires are coming through this bracket, and this bracket is what holds the entire assembly in the chassis. But before I can put this bracket on the PA unit, I have to close the PA unit up with this cover, and before this cover can go on, this whole wire harness has to get done. But this wire harness has to go through this hole in this bracket. So this bracket has to be off, sort of, while I get all these wires in place and I get the cover on. And then once I get that all together, I have these little half holes to put a screw through that tab, and I have 1, 2, 3. No, I have 2 on the side here somewhere. Okay, but these 2, I have these little half holes to get through that much thickness. So about 2 and 2.5 inches. So it's pretty hard to get to these screws. But it's pretty hard to get this thing back together. But yeah, not for the faint of heart. Not a nice assembly. I much prefer working on some of the Kenwoods with the whole finals unit. Just tips out the back, fan and all. Okay, moving on. Okay, we got it all back together, and for the sake of honesty and maybe comedy, I have to tell you, I made a mistake that's kind of funny. That is a little tiny jumper, the kind of little push-on jumper that you see on computer boards for bridging 2 pins. Is a little jumper for the driver bias that I forgot to put back on the board. And if I go back in the videos when I edit this, I'll probably see that. To see if you noticed that, you can go back. Anyway, took it all apart, put the jumper back on, powered it up. Everything looks really good, and I'm really surprised at how clean this radio is. Now, I don't know if we really discussed why there's an A mode, a Class A versus a Class AB mode. Well, I'm going to show you why. This radio was really designed for contesting, and the thing about contesting is it's frequently a group activity, and you'll get multiple operators, certainly at field day, but you'll get multiple operators operating on different bands from the same location. And under those circumstances, even a signal at minus 40, 50 dB down from 100 watts right in the near field is devastating. I mean, if you're trying to operate on 20 meters and the guy next to you is sending CW on full tilt CW on 7 megahertz, I mean, his key clicks are going to be, they're going to be all over the place. You're not going to be able to operate on 20. So Yaesu came up with the idea of putting a Class A mode in the transmitter to really clean it up, to get another 15, 20 dB, whatever. I didn't look at the specs, but it's pretty clean. And I'm really surprised. They've got a nice low-pass filter here. And I'm going to show you, as soon as I get this other camera going. Here we have our spectrum analyzer view. And this is a 50-watt signal with, that's Class AB. And you see the second harmonic and some other mixed product that may be internal to the scope is visible just on the right, those 2 little pips on the right. And if I go into the Class A mode, they're gone. The output drops about 12 dB. Even accounting for that 12 dB, if I turn up the RF gain, bring it back 12 dB, should be cleaner than that. I'm a little surprised. Okay, so the higher harmonics are definitely cleaned up at full output. Yeah, so it's definitely cleaner in A mode, but not as much as I would have expected. The second harmonic, I would have expected that to have gone away. See, that's almost as high. There's AB. There's the AB mode, and we're down about 58 dB. 58? Yeah, we're down about 58 dB on that second harmonic. And then when I go to the Class A mode, bring the fundamental back up, we're down a tiny bit more, but not more. But certainly the higher harmonics, if you look above that, there's nothing. And I go to the AB mode, and of course now now I have these higher peaks over here. So it definitely does something. Not as much as I would have liked, especially at the second harmonic level. I don't think that's a significant enough difference to justify, you know, blowing 150 watts out the back of the radio with no with no RF. I would have expected it to have been cleaner than that, but that's what it is. And everything looks fine otherwise. And we tested the receiver, and let me show off the lab here. By the way, that's an old HP 141T spectrum analyzer with the 8553 and 8552 plugins on it. The RF section, I'm using the lower frequency RF section, 110 meg section. I have an 18 gig section in the box, and I basically don't use it unless I really need it. I can jury rig a front end mixer on this 110 megahertz unit if I have to. I can't replace the mixer in the 18 gig unit if it gets blown out. I've already blown one out, and they are as scarce as hen's teeth now. Okay, let me just swing you over here. On the signal generator side, this is kind of cool. Piece of equipment you may not see too often. This is a Boonton, made in Boonton, New Jersey. This is a Boonton RF signal generator, and it does quite a few functions. It's got plenty of memories, which is convenient because I can program steps for tuning the radios up, so I can go you know, 1.9, 3, 7, 5, 7, 14, 21, 28 megs, and so I can go up and down through the bands, and I can step through those automatically. I can also do sweeps. I have a variety of sweep functions. I have FM modulation, phase modulation, AM modulation, various levels and frequencies. In fact, if I go to, there we go, AM frequency 400 hertz, level 50%, and I should have, no, it's not connected. Okay. There we go. So now you can hear a level. And I mentioned before that I use a an RF tap that has about a minus 42 dB attenuation. So I'm able to, like, if I can show you that, it's back there, that little silver box. That's my RF line tap, and so I can run at minus 42 42. I can run my signal generator and my spectrum analyzer at the same time. You can see over here, the spectrum analyzer is showing that signal. I can see it disappear. So I can run my transmitter and my signal analyzer at the same time. I don't have to worry about them burning each other up because I got 42 dB of attenuation there in the RF line. And I just compensate for that when I make my readings. I compensate for that with the level here. So I just, you know, add or subtract 42 dB to that. And I also mentioned that whenever you run any equipment, any test equipment, whether it be signal generators or spectrum analyzers or whatever, that you always protect your equipment. And here I have a 50 ohm 10 dB pad, and clearly labeled 50 ohm 10 dB pad, which we make sure we test and calibrate every once in a while. And that 10 dB, as you can see on this screen, that 10 dB is nothing. I've got 40 dB of attenuation on the attenuator anyway, so an additional 10 dB is really nothing. So protect your equipment, play it safe. So this radio is done. It's working fine. I don't know how to turn the display brightness up because I need it brighter than that. But there you go. We left nothing to chance. Whoop. We really left nothing to chance here, which is the way I like to work. I don't like any surprises. I certainly don't want another episode where I blew up the ICOM because my static wrist strap had developed an open circuit in the resistor. So there you go. It's been a long time getting here, but this the third and last episode is finally done. Thanks for watching. Please share with your friends. Talk amongst yourselves. Bye for now.